How are organic molecules different from each other? What distinguishes one molecule from another? If they all had CC, CH bonds, carbon, 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 hydrogen bonds. Well, the only distinguishing feature here is functional groups. So functional groups they could be atoms or groups of atoms that come with different characteristic chemical and physical properties. The most important part here is that they are the reactive part of the molecule. And not only that they determine the reactivity or they drive reactions, but they also determine the molecular geometry, physical properties, like we said, reactivity. In fact, this chapter is a foundational chapter. That's why it's the third chapter. And it is going to help you learn about these different functional groups. And for the rest of organic chemistry, and so this semester and next semester, if you need to take organic chemistry 2, is going to be about the different reactions and their mechanisms of those different functional groups. So we're going to learn about the reactions of alkenes and alkynes and alkyl halides. And of course, next semester will be about carbonyls and carboxylic acids, etc. So what are the two types? Well, you have one with a heteroatom. Those are atoms other than carbon or hydrogen. Anytime in organic you hear heteroatoms, you know that these are non-carbon, non-hydrogen atoms. So they're like nitrogen, oxygen. These are the common ones, the most common ones, the nitrogen, the oxygen, and the sulfur. And then you have pi bonds. Pi bonds are easy to break, and they again drive chemical reactions. So let's look at an example here. You have a heteroatom right here, that's oxygen, and attached to, let's say, a carbon, and you can continue the rest of the carbons if there are some. What makes it different, or what makes it more what we call reactive here? Well, if combine what we learned so far from the previous two previous chapters, we learned that oxygen is very electronegative and it has lone pairs on it. So when it has lone pairs on it, it's going to be nucleophilic, meaning it's going to donate this lone pair or one of these lone pairs. And of course, if it's electronegative, because it has a 3.5 and carbon is a 2.5, it's going to draw electron density away from carbon, making carbon electron deficient. Here's an example of the pi bond where it's an alkene here, what we call alkene. It gets easily broken. Pi bonds are not as strong as sigma bonds, so they would rather actually go and form sigma bonds. Well, in the process here, they have to donate, one of those, the pi bond, which makes it a nucleophile or a Lewis base. Nucleophile is what we're going to use for what we call a Lewis base. So I say usually is that carbon, 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 hydrogen bonds are boring bonds. Really, they are boring bonds. There's not much going on here. So what makes a compound different is the functional group. So it always goes this way. You have a carbon skeleton, there's a bond, and then there's a functional group, which is sometimes shortened for FG. So again, boring part, the exciting part. Now, that's not to say that these carbon skeletons are not important. Didn't say anything about that. Of course, they're still important because structure determines reactivity. That can actually have an effect on the reactivity of the functional group, even solubility. So let's give you an example. Down here, let's draw that down here. I'm going to really just show you a simpler example, and then I'm going to use the skeletal structure. So let's say we have this right here. And now you know why we would rather use a skeletal structure, because it's much shorter to do that. It takes us a lot less time. Right here. So if I have all right away, where is our carbon skeleton, or what we call, sometimes I learned it as what we call the backbone, the carbon backbone? Well, it's all of the ones that are highlighted in yellow. Carbon, 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 hydrogen bonds. So this is all the carbon skeleton. In yellow. And once again, it's unreactive. Now, in green here, this is my functional group right here. And that would be the, so let's write that down. This would be the functional group. And it's the reactive part. Well, let's look at what makes it more important in this sense, or reactive. Well, we know that nitrogen is more electronegative. So in this case, we're going to put the delta minus on N, and of course, put the delta plus on this C right here, this C. So number one is that N makes adjacent carbon delta plus, or electron deficient. There are lone pairs, or there's a lone pair on O, on N. N has a lone pair. Which makes N a base. And then finally, these H's, one of them, the N has acidic H's, or protons. So that's what you learned from the last chapter. You're applying it here. So in the next video, you're going to learn about the different types here, and then we're going to actually start working on an example.